We live in an era where AI can seemingly optimize literally anything, right? Supply chains, delivery routes, traffic patterns, you name it. But when it comes to liquid bulk logistics, standard software just hits an absolute brick wall. Or actually, it hits the immutable laws of chemistry and physics. Let's dig right into this explainer and see why generic AI fails so spectacularly in this space.
Right off the bat, we've got to establish the wildly different stakes here. I mean, a simple detour or a fender bender for a standard dry van, it probably just means some late groceries. Maybe you lose a couple pallets of Cheerios, it's really no big deal. But for bulk liquids, an improper route can trigger a multi-million-dollar factory shutdown, or worse, a massive hazmat crisis with raw materials washing across an interstate. It's an entirely different ballgame.
So to really unpack why this is so insanely complex, here is our roadmap. 1. Dry van versus liquid bulk. 2. The generic AI routing flaw. 3. Risk 1. Thermal degradation. 4. Risk 2. Weight and bridges. 5. Risk 3. The plant gate. And finally, smarter liquid bulk logistics.
Let's start with Section 1, dry van versus liquid bulk. We really need to look at the fundamental difference between shipping a box and shipping volatile chemicals.
Because if you treat an ISO tank like a standard box trailer, you're doomed from the start. Look at the economics alone. You aren't booking by the pound, you're booking by the gallon. Volume is literally everything here. And the equipment? A standard dry van runs you what, 35 to 40 grand? A liquid tank trailer is easily upwards of $100,000. Throw in the mandatory deadhead miles for intense tank washes between every single load, super strict hazmat endorsements for your drivers, and a minimum of $5 million in liability insurance? Yeah, you can start to see why this requires a completely specialized approach.
Section 2. The generic AI routing flaw. Because when you try to force this highly specialized freight into standard off-the-shelf routing systems, things break down incredibly fast. See, standard AI optimizes for speed. It looks at travel time, distance, and basic dock hours. And hey, that's absolutely fantastic for standard trucking, but it completely misses a crucial detail. We are transporting a living, breathing, and sometimes highly volatile substance. A generic algorithm just doesn't know that 50,000 pounds of sloshing liquid reacts entirely differently to a crosswind than a trailer stuffed with paper towels.
It really comes down to this court truth. Liquid seeks its own level. You literally cannot bargain with physics. The cargo won't behave like a neatly stacked pallet, and as we're going to see right now, when routing software ignores this massive inflexibility, it creates 3 huge operational risks.
Section 3. Risk 1. Thermal degradation. Let's see what actually happens when the clock is ticking on chemical stability.
This isn't just about arriving on time. It's about what physically happens to the product if a detour takes too long, especially in the cold. Let's say a generic AI says, hey, take this scenic mountain bypass. It'll save you 40 minutes of traffic. What the algorithm doesn't realize is that the ambient temperature on that mountain pass is 20 degrees colder.
And extreme temperatures are a literal nightmare for bulk liquids. Too hot, you risk severe product degradation or super dangerous overpressurization. Too cold, the chemicals can thicken up or completely solidify, ruining the entire shipment if the truck's in-transit heating systems just can't keep up with that unexpected icy delay. Here's a crazy real-world example from our sources. The 40-foot mothball. A shipment of molten naphthalene hit a delay and suffered a heating system failure. The chemical cooled down, set up, and literally turned into a 40-foot solid mothball inside the trailer. Just imagine this. It took workers 2 full weeks of physically chipping and shoveling out this massive solid block just to salvage the trailer itself. We're talking tens of thousands of dollars loss, suspended factory lines, all because the physical thermal limits weren't perfectly managed.
Moving on to Section 4. Risk 2. Weight and bridges. Next up, let's look at how the sheer physical weight of liquid totally shatters standard AI route planning. 80,000 pounds, or roughly 44 tons. That is the strict, totally unforgiving Department of Transportation limit for gross vehicle weight. So once you factor in the incredibly heavy tractor and the specialized tank trailer itself, you can actually only load about 45,000 pounds of liquid inside to stay street legal.
When you look at the immense scale of these rigs, you realize exactly why high center of gravity rollovers from crosswinds are such a constant threat. And bridge weights. If a generic routing AI spots a nice little shortcut over a county bridge, it'll confidently send the truck that way. But if that bridge isn't rated for 80,000 pounds, or if the new route involves high crosswinds that destabilize all that sloshing liquid, well, the software just handed you a potential disaster.
And here is where it gets truly wild. Liquid weight cannot be shifted. Look, if you're in a dry van and a weigh station says your rear axle is too heavy, you just open the back doors and move a couple pallets forward, right? You absolutely cannot do that with a liquid. It seeks its own level. In the past, when strict weigh station inspectors would flag a liquid bulk truck for being just a few pounds over on one specific axle, the drivers actually had to manually pump out their own heavy diesel fuel and give it away just to rebalance the vehicle's total weight profile. Generic AI is completely blind to this.
Section 5. Risk 3. The plant gate. Our final risk is all about the destination, where an AI's promised ETA means absolutely nothing if you can't physically unload.
Generic software calculates a simple drop-off time, assuming you just bump a dock, a forklift unloads the pallets in 30 minutes, and you're gone. But liquid bulk unloading at a chemical plant is a highly engineered, rigid, and surprisingly delicate operation.
These steps are strictly non-negotiable. Unloading takes specific hoses, specific fittings, and totally specific atmospheric conditions. For instance, if you're using a pump to suck the product out, the driver has to ensure the top dome of the trailer is completely open to let air in. If they forget, the vacuum pressure will literally crush the heavy metal walls of a $100,000 trailer inward like an empty soda can. On the flip side, if you use a compressor to push the liquid out, that dome better be perfectly sealed tight.
A generic algorithm has no idea if the driver needs a pump or a compressor or if the facility even has the right fittings ready. And when there's a mismatch, you get massive demurrage cascades. Demurrage is that painful penalty fee you pay for delaying a truck at a site. So if a plant requires a 40-foot hose to reach the tank, but the driver only brought the standard 20-foot one, the whole delivery just halts, the schedule is destroyed, and those penalty fees skyrocket, as everyone literally just sits around waiting.
Algorithms just assume a fast drop-off. But our sources detailed this amazing story, the mystery of the twisting pipe. A paint factory couldn't figure out why their deliveries always took 4 to 6 agonizing hours to unload. Finally, a broker went out there and discovered a hidden physical reality, a 600-foot extension pipe winding all the way through the factory that the liquid had to be pumped through. They finally installed a short, direct line, and unloading dropped by 3 hours instantly. There is no AI on Earth that could have predicted a 600-foot pipe bottleneck just by looking at a map.
Finally, Section 6, Smarter Liquid Bulk Logistics. So how do we actually bridge this huge gap between smart software and the heavy, unforgiving laws of physics? It's simple. We need custom, specialized routing solutions. Generic AI only cares about travel time and basic capacity. But a true liquid bulk routing platform must be AI first, but strictly physics-bound. It has to integrate thermal limits, precise axle weights, hazmat tunnel restrictions, and complex gate procedures in real time. It needs to know exactly what fittings are waiting at the plant gate before the truck even turns the ignition key.
So I'm going to leave you with this provocative thought. How do we balance the massive push for total software automation with the immutable laws of chemistry and physics? Because as tech keeps advancing at lightning speed, we really can't forget that our software still operates in a very heavy, very physical world. Elegant code is great, but it cannot negotiate with a freezing tank of chemicals or a 600-foot twisting pipe. Thanks for joining me on this explainer, and honestly, I hope it completely changes how you look at those massive tankers rolling down the highway next time you're out there on the road.